Welcome back to Let's Code. I'm Chris Biscardi, and today we are going to recreate this sketch in Nannou and Rust. This sketch in particular is showing a graph of Perlin noise in about 6 octaves combined to give us an output that is, if you're familiar with games like Minecraft, reminiscent of the way that the land is generated. Anytime we click on this sketch, we get a new seed in the bottom right. That's what Perlin noise is. Perlin noise is a seeded pseudo-random number generator where each of the values next to each other are kind of related. So we don't see this algorithm ever jumping way too high or way too low, or from all the way at the bottom of the screen to all the way at the top of the screen. It always follows this path that is sort of a little bit related to the points that were defined next to it. And every time we click, we get a new seed and the start changes. So in this case, we went down, we stayed flat a little bit, and we went up. If we change the seed again, we go up, and then we start going back down. So this algorithm is super useful in a number of different ways. And today we are going to be graphing the single dimension version of it. Now, the first thing I want to point out about Perlin noise is that Perlin noise is not random. So this is a visualization of the exact same that we were just using on the Perlin noise, but this is generating random values every frame. And you can see that this is a lot more frenetic. It's all over the place, right? The values don't connect to each other. If you used this to generate terrain in a game like Minecraft, this would be pretty awful terrain to walk around on, although, who knows, it may look good. And of course, we can compare that with a plain Perlin noise. Ignore this vertical artifact here. That's just because I made the window bigger. So you can see that in a single dimensional Perlin noise of 1 octave, so this is only one iteration of the Perlin noise algorithm, we get this very smooth kind of looping, almost periodic graph. And this isn't too interesting itself, which is why in the example that we're going to create, we're actually going to run this algorithm 6 different times. So the idea here is that we take the X value that we are at, which in this case happens to be the number of frames that have run since the program started. We put that into the Perlin noise algorithm, and we get out some number that is kind of related to the numbers around it. And again, since Perlin noise is seedable, we can enter a different seed, in this case, BRAI. I chose a number of letters because that seems to be more human readable or human understandable. You can use CHIL, and we get a different one. Use NIFT, and so we have a U32 amount of seedable space here to generate different worlds or terrains or tile sets or whatever you want to generate here. I also mentioned octaves earlier for our primary example. And this is what I mean by octaves. You can see the original Perlin noise algorithm at the bottom here. This is the one that we just looked at on our screen. And each time we go up, we're basically just increasing the X coordinate by some power. So X to the second power, third power, fourth power, etc. And in this case, I have it running at a scale of 2 to the iteration power. So 2 to 0, 2 to 1, 2 to 2, 2 to 3. So we get a kind of effect where the values that we're getting out of the noise are skipping larger and larger areas. So they get a little bit more erratic, a little bit more frenetic as we go sort of up this frequency chain. And to get the end result that we kind of want to combine all of these. So we don't just want this like really smooth Perlin noise, but we also don't want this like really choppy Perlin noise up here either. So the way that we combine these is going to be the bottom Perlin noise is going to have the most effect. It is going to be sort of the definition for the mountains if you're thinking about kind of Minecraft landscapes. And as we get higher and higher and higher, we're going to say maybe these are boulders or something like that. And as we get all the way up here, these are just like pebbles or pieces of sand or something like that. So we want the more frenetic, more energetic Perlin noise to be less impactful on the total algorithm, while the larger sweeping Perlin noise is going to be more impactful. And we actually do have an easy way to do this in Nannou, which is really interesting. And of course, we can click on this. We can change the seed whenever we want to, and we will always get sort of the same values for the same seed, which is really important, especially if you're saying creating Minecraft worlds, right? Where you want to be able to share a seed with your friend and have them actually explore the same world. But we do get variations amongst the different frequencies as well. So to refresh your memory, this is the actual code that we are going to write today. It is the combined 6-octave Perlin noise graphed from a single dimension into 2 dimensions. So the X value is our input to this Perlin noise algorithm, and the Y value is the output. Now, of course, we need a new Nannou project. And in my case, I have all of the examples as well inside of bin, which you can find on GitHub in the description if you would like to look at those. In here, I have a number of dependencies. We can get rid of this Perlin noise dependency because we are using the noise from Nannou. So in our case, we really want Nannou especially. I use Chrono for saving out file names. I use names for generating the new seeds. And then rand was the other example that I showed earlier to show the randomness compared to a noise algorithm. In our main.rs, we have a number of interesting things happening. At first, we set this noise step, which I'll kind of explain later, but the TLDR on the noise step is that this Perlin noise algorithm is periodic. So if we take a look again at the plain Perlin noise example, we can see that it will actually cross over the 0 point at any integer. So if we have our X value and it's equal to 1, 2, 3, 4, 5, 6, etc., we actually won't get anything out of it because the number that comes back from the noise is always 0. So in our case, if we remove this noise step right here, this divided by noise step, so we're taking the elapsed frames, the number of frames that have occurred in our program so far, and we are dividing it by the noise step, which I've set to 500. We remove that and I rerun the basic Perlin example. What we're going to get is just a straight line because the only values we're graphing are integers. And if we pass an integer to the Perlin noise algorithm, its output is always 0 because that's just inherent to the way the Perlin noise algorithm works. So that's why when we set this noise step here, we're saying that we want 500 values for every integer. So we're taking 1/500th of a step on the noise algorithm every time we ask for a new value. So we've got 0.002, 0.004, and so on. This will give us a number of values in between 0 and 1 and in between 1 and 2 so that we actually get the interesting flow of values from the noise rather than constantly hitting on where it happens to be 0 all the time. Of course, we have to set up our Nannou app. So we set it up with our model function and our update function, and then we run it. And that's really our main function is super small. Now, our model will contain the noise generator. In this case, it's basic multi, which we'll go over in a second. The vec of points that we are going to graph. So all of the values that we've pulled out and all of the inputs that led to those values. So if we have, say, 1 and we get out 0, that'll be 0.10 in this vec. And then frame start is something we'll cover in a little bit. Frame start is basically anytime we want to reset the seed, we need to start from 0 again, but the elapsed frames for the entire program run haven't changed, right? They just increase forever. So we need to subtract, hey, when did we change the seed from the total frames, which will give us a complete start over for each seed. Our model function just sets up our model. So we don't actually need to keep the window reference around. So we've got a little underscore there, which is a Rust convention. And we just create a new window with a new size of 1200 by 630. These are in pixels. We set our view function, which is where we do all of our rendering and drawing. And then Keypressed and mousepressed are 2 utility functions that we'll go over later. We build the window and we unwrap it because you have to use results in Rust. And then we return our model. So we've instantiated our new basic multi-noise algorithm. We've instantiated our points to be nothing yet. It's just an empty vec. And our frame start is 0 because we started at the start of the program. Now, basic multi is interesting because it is Perlin noise, but it is a set of Perlin noises, just like we were showing before. So we showed 6 different Perlin noises operating at the same time. Basic multi takes all of those 6 octaves, as they're called, and combines them in a specific way to get that nice flowy Perlin noise with the higher frequencies having a little bit less effect on the total value. This is how we get our mountains for the original Perlin noise, and then we get our little rocks with the higher frequencies. We can, of course, control how many octaves or any of the other values as well, but we don't need to do that today. I'm just going to use the defaults other than changing the seed every once in a while. So again, this is 6 Perlin noise algorithms all operating at the same time. being combined into a single value. So our update function runs before our view function. Our update function is responsible for creating the set of points that we actually want to graph in our view. So for us, we're going to grab the size of our window rectangle from the app. This will give us the size that we can map from -1 to 1 to the window size so that we can actually show something on screen instead of having it be really small. This will be called on basically every frame. So the current step is going to be the number of elapsed frames minus the frame start, which, for our initial iteration is 0. If we ever change the seed, this frame start gets set, and then this will be something different. But this will give us the number of frames that have elapsed for the particular seed that we're using. So if it's the original seed, which is usually 0 when we start the program, this will come out as just elapsed frames. And if, say, at frame 1000, we decided to change the seed, what would end up here is we'd get app.elapsed frames, something like 1500 maybe at some point, minus the frame start, which would be 1000. So we've only progressed 500 frames. And then we would divide that by the noise step, which is 500 in this case. So the current step would be 1. And this current step increments by 0.002 because we've set this noise step to 500. So 0.002 is 1/500th of 1. We take that current step and we turn it into an F64 because it's an F32 by default, which I can prove by showing the inlay types here. Current step is an F32. But our noise function, the Perlin noise, wants us to use an array of 2 F64 values. So we just convert that up because an F32 fits neatly into an F64. So there's no problem. Now, the noise algorithm we're using here is actually a 2D Perlin noise. So what I've done to make it a single dimensional Perlin noise is I have taken the liberty of setting the Y or the second dimension to 0. So it'll never change. So we only have one changing dimension of the noise. Once we get the value out of the Perlin noise, which is going to be a value from -1 to 1, we can map that value that we get back, which is from -1 to 1, and we can map that to the top and bottom of our window. So basically, when we graph our Perlin noise, the bottom of the Perlin noise is going to be near the bottom of the window, and the top of the Perlin noise is going to be near the top. And then, of course, our model has a points array or a points vec. An array is what you would call it in, say, JavaScript or something like that. And we just push a new vec2 with the current step, which is our X value. So something like 1.02, and the mapped Y value, which is the Y value we got from our noise distributed along the height of the window. And then we just get this nice big vec basically of points that we need to graph, which brings us to our view function. Our view function is responsible for actually getting these onto the page. We have a background color and a foreground color here. These are both some shade of pink or purplish, depending on what you want to call them. We again set up our two sort of containing rectangles here. So we have the rectangle that represents the entire window that we'll be rendering in. And then we have another rectangle that represents a padded window inside of that. So in this case, we have the original window. We pad that by 25 pixels. So it's about 50 pixels smaller in both directions. And we set that as WinP rectangle. We need to grab the draw instances, which is like our canvas, basically, because if we are in our view function, we need to be able to draw something. We set the background color to the background color, and then we start drawing a line at x equals 0. The line at x equals 0 represents the, whoops, that's not an x equals 0 line, actually. So we start drawing a line at y equals 0, and we draw it horizontally across the entire window. So this is the 0 point. Our Perlin noise will result in numbers going up above this and down below this, but it will always return through this 0 point on the y-axis. So we take the entire window and we get the left and the right sides. We start the line at the left side, we end the line at the right side, we color it. So we get this horizontal line through the middle of our graph, basically. The noise line is actually going to be a polyline, which will allow us to set up a bunch of points that then Nannou will take care of graphing or drawing between. In this case, to get that graph moving off the side effect that we can see in the Perlin noise, this kind of like the graph dot that we're currently on is always in the middle, and the rest of the graph moves off to the left. To achieve that effect, we are going to have .x be 0 minus the number of points that we've already created. And then down here, when we iterate over all of the points, we're going to use enumerate to turn each of our X positions into basically a pixel. So what we're doing here is we're offsetting the graph by the number of points that we've created already. And we're also rendering each point as 1 pixel. So this, as we build more points into this line, the line moves further to the left, keeping the current position always in the center of our screen. And we also set the weight and the color of this line. Now, it's interesting to note that we take model.points, we iterate over it here to get an iterator, and then we use .cloned to get owned values here. Basically, when we are iterating over these points, the original X value isn't the value we want. We want to be able to change point.x. So to do that, we need to own these values. It can't be references to the original points array or the original points spec. So we do that, we enumerate, which gives us the index in addition to the point. We can set point.x on our new owned point and then return the new point. And that allows us to collect into a vec of vec2s, which is just a vec of points that we now own. And we can give to the polyline to draw. To get the dot at the edge of our function, we set the X to 0 and we set the Y value to whatever Y value is the last point that we created. The X at 0 will place this dot in the middle of our screen horizontally while iterating over points and grabbing the last one, which potentially could not exist if, say, this was an empty iterator or something like that. So we unwrap and we get the Y value of that last point. And this will keep the dot drawing in the middle of the screen, but going up and down as we create new points. We set the width and the height to 10 pixels, and we set the color again to the same foreground color we're using everywhere else. Now, this bit of code here is responsible for drawing some of the horizontal lines we can see if we shift into a different seed. It doesn't always work. I didn't quite finish this piece of the code, but you can see the lines coming in. These lines are drawn exactly at all of the integers for our Perlin noise. So you expect that this Y value for the Perlin noise, because it's 0 in every Perlin noise call, that it will always hit this cross section right here. No matter where it is before that, I always know that at every integer, because Perlin noise functions return 0 at integers, it will always reach the 0 point on the X and the Y axis every single time. And finally, we want to be able to display the seed that we're using in the bottom right corner. So in this case, we are viewing loud here. It's useful to know the seed in case we ever find something interesting enough to save, because we can always feed this seed back in. And what I've done here is I've taken 4 characters, and our seed is actually a U32. So we turn that into a U32, which we'll go over in a little bit. And we feed that into the algorithm. And then we get that back out and we turn it back into characters. Model.noise.seed gives us that U32. We need that seed to be a byte array because we can use standard stir from UTF-8 and pass in that byte array to get back a string slice. And that string slice can be used when we draw some text on the page. So we're going to use this seed display. We're going to set the font fairly large. We're going to set the width and the height to the width and the height of the padded window from earlier, so 25 pixels in from the sides. We're going to right justify it, and we're going to align it to the bottom of the screen because it's in the bottom right. And then the color is going to be the same foreground color we've used everywhere else. And having finished all of our drawing logic, we can draw everything in this frame to the app, and that finishes up our view. Now, there are 2 other interesting handlers that I have in here. One is Keypressed, which I got the idea from a friend. So thank you, Xander. In this case, I set chrono offset local now to now. And if I ever press the key S, then we go into the main window, we capture a frame, we name it the name of the exe, which happens to be the name of the binary. We add the date time to that file name, and we add PNG at the end. So this is 3 display formatters. This is our first value, this is our second value, and this is our third value. So we get a Perlin noise 1D. Oh, I should add a dash in there now that I look at that. We get the executable name, we get the date time, and then we get .png right on the end. So that's really nice. So if I ever see something super interesting, I just hit S, I get a write out of the PNG at that moment. And throughout the course of this video, you see me click on this quite a bit. Every time we click, we want to create a new seed for our noise generator. In this case, we use the generator from a crate called names. That generator gives us something that is like word-word, of which we cut the first 4 characters off and use those. So we ask the generator to give us the next seed. It gives us one. We turn that into a byte array. So this is an array of 4 U8s, which are bytes. We loop over the seed that we've been given, which is a string. We turn that into bytes. We iterate over it. We take 4 of the bytes and then we enumerate, which gives us the index of each of the bytes as well. And then this array is something that we can set inside of this loop. So at each of the indexes for each of the bytes, we set the byte at that byte to the value of our byte, which is a lot of bytes. And then after we do that, we have this byte array filled, which we can then throw into the U32 from big endian bytes function, which will give us an actual U32 here. And basic multi needs to be instantiated again as well. So we instantiate it and then we set the seed on basic multi, which at the top of our file, you'll see this seedable trait. We need that trait in scope to be able to run set seed on basic multi. But other than that, all of this comes out of Nannou itself, or is re-exported at least through Nannou. Once we have our noise, we set our noise to the seeded noise. We set our frame start to the current elapsed frames, like we talked about earlier, to restart our display. And then we set our points also to an empty vec so that we can start re-instantiating. And that leaves us with this. We get this nice Perlin noise of 6 octaves rendered to the screen. And every time I click this, we get a new seed in the bottom right, and we can watch our Perlin noise go. So that's about it for this video. I'm going to leave the links to the GitHub repo in the description below if you are interested. If you have any questions, you can reach out to me on Twitter or in the comment section, or even just file an issue on GitHub, and I will try to answer it. And I hope that you have fun creating some Perlin noise. I'll see you next time.